Welcome back. In this video, we're going to look at an example of applying the FMA method and the principle of moments to a system of particles. So I'm using an example from a textbook problem, and if you want to refer to the textbook, the number is 1055. There's a lot of detail to start off this problem. Given a whole lot, find just a few things. So you may want to take some time to pause the video and record these things, but I'm going to walk through it, and so feel free to capture all the details. Basically, what we have in the setup is we've got a system of particles, just 3 in this example, and we want to find the position of the center of mass, the velocity of the center of mass, and the acceleration of the center of mass. So position, velocity, acceleration are typical motion variables. So in this system, we just have, as I said, 3 particles. P1 is 6 kilograms, P2 is 10 kilograms, and P3 is 4 kilograms. Mix those up. So that's what I have here for P1 is 6 kilograms, 10 kilograms, and 4 kilograms. The position of these, if this is difficult to view a 3D image on a 2D surface, is for number 1, it's 8 meters back in the x direction. So the position is negative 8i meters. Similar for number 2, 5 down in the z and 4 down in the y. So that gives us negative 4 in the j and 5 in the k. Particle number 3 is positive 6, back 8, and up 6. So that gets us 6i, 6j, and negative 8k. And then in the setup of this problem, we're told that about the forces, external forces acting on these particles and the velocities of these particles. So for convenience, thankfully, each particle only has one force acting on it, and those are recorded here. So F1 is a force of 60 in the j, negative 60 in the j, and 90 in the k newtons. F2 is negative 50 in the I, 100j, negative 100j, and negative 40 in the k newtons on particle 2. And particle 3 is 30i and 40j newtons. The velocity of particle 1 is 4i and negative 6j meters per second. Velocity acting on number 2, particle 2 is 5j and negative 3k. And finally, the velocity of 3 is 2i and negative 7k. So that's a lot of detail to capture, and unfortunately we're going to need all of it in order to do these 3 steps, which is to find position, velocity, and acceleration. So go ahead and capture that information, and then we can move forward. So let's begin our solution process. So you may recall that the principle of moments can be used to find, to relate the position and the total moment acting on the center of gravity based on all the sub-moments. And the velocity can be found in the same idea from the principle of moments, that the momentum of the whole system is all of the little bits of momentum added together. So for RG and VG, position and velocity, we're going to use the principle of moments to find those. And for acceleration, we're of course going to use the whole point of this topic, the force method, force mass acceleration method. All right, so let's begin and see how this would look. So recall that the sum of all of the little bits of moments, mi, ri, has to be equal to the sum of the total and the position of something of interest. In this case, we'll talk about the center of gravity. So for us, let's see, the total mass is going to be the sum of all of the masses. So 6 plus 10 plus 4 is 20 kilograms. And so 20 kilograms times the vector wherever our center of mass is has to be equal to all of the little bits. So that would be m1 times the vector r1 plus m2 times the vector r2 and m3 times the vector r3. This is going to get pretty messy, so I'm going to summarize the steps here. But m1 and r1, multiply those together. So 6 kilograms times -8, and we're going to get -48 acting in the I direction from this portion. For 2, we have 10 kilograms and multiplied times -4 and 5. So that would get us 40 on the j direction, -40 in the j direction, and +50 in the k direction. And then we'll do the same thing for particle 3, 4 times 6, 4 times 6, and 4 times -8. Add up all of the j's and all of the k's, and then divide out our 20 kilogram mass, and we'd be left with what this position vector is. So it turns out, if you want to do this calculation, our position vector of where that center of mass is -1.2 in the I direction, -0.8 in the j direction when you add up those pieces together, and 0.9 k in the k direction. So, let me make sure that's positive. Positive 0.9. Meters. So at this point, so this was one of the things we wanted to find. So at this point, it's good to make sure that that guess seems reasonable to us, or that answer seems reasonable. So -1.2i, -8j, and 0.9 in the k. So just thinking about where this would be, so we're going to go back 1 in x, going to go down close to 1 in the j, and move down in the k, or in the z direction, pretty close to 1. So I would say our center of mass looks to be somewhere in this region. Maybe a little on the other side of the z-axis might make more sense. And just looking at it, kind of distribute the weights, it would make sense that it's kind of headed towards P2, because P2 is a little bit more massive than the other two, close to twice, or more than twice in the case of P3. And then it's also kind of geographically in the right location. So if you found a center of mass way over here, something went wrong, right? So you want to check that, kind of put where the center of mass is on your diagram and go, okay, that seems like a reasonable answer. All right, so that was using the principle of moments. We found the position. We can now do the same thing and apply the principle of moments to the momentum. So all of the momentum of the particles, VI has to be the total momentum of the center. So again, we can take that total mass, 20 kilograms, times whatever our center of mass velocity is going to be. And it's going to be in the same exact approach. So the mass of 1 times the vector of the velocity in 1, plus the mass of 2, vector of the velocity of 2, and the mass of 3 times the vector of the velocity of 3. So this process is exactly the same as here, so I won't go into all the details, but again, mass of 1 times velocity of 1, so we take 6 kilograms, and this time we multiply it times 4, we get 24i, 6 times 6 is 36, so that's -36j, and we get an I and a j component from 1, ijk for 2, ijk for 3. Add up all the pieces and divide out your total mass, and you come up with the velocity of the center of mass. So the velocity of that center of mass, following these number systems, you should find is 1.6 in the I direction, 0.7 in the j, and minus 2.9 in the k. And that should be meters per second. So we've just applied the principle of moments twice, found a position, found velocity, and now the last part is the part that's of interest to us, right? Which is applying the force mass acceleration method, FMA method. So that FMA method says that the sum of the forces equals the total mass of our system times the acceleration of that mass center. So again, we could write this out and say that 20 kilograms, the mass of our total system, times the acceleration of that center has to be equal to F1, the external force acting on 1, plus the external force acting on 2, plus the external force acting on 3. So some of these components, so we'd take negative 60 over here in the I, plus negative 50 in the I, and plus 30 in the J. Put all those together. Take the, there's no J component for F1, so take 100 and 40, you get negative 140, and then K, you get 90, minus 40, and then minus 0, because there's no K component of F3. So out of all of those pieces together, divide out your mass again, and you'll come up with the acceleration of that mass center. So the acceleration of that mass center, if you compute these numbers, turns out to be minus 1 in the I direction, minus 10 in the J direction, and positive 25 in the K direction. And the units for that, of course, will be meters per second squared. So to review what we've done, given quite a bit of information to start off with, our goal was to find position, velocity, and acceleration. For position and velocity, for a system of particles here, it made most sense to use the principle of moments, which is that all the moments of all the little pieces have to be the moments of the whole thing. And the principle of moments in terms of velocity is all of the momentum, little pieces of momentum, have to equal all of the momentum of the whole system. So that made sense for the position and velocity. And to find acceleration, of course, that is when we needed to apply our FMA method to a system of particles. In this case, pretty simple. Just add the forces up by components in each direction, and then divide out that mass, and you found the acceleration.